Good morning, everybody. Welcome to day 3 of Optimizing the Effort of Others. I guess we'll get started. So the theme of the day today is contracts, algorithmic combinatorial, and algorithmic delegation. So we've got 2 sessions today. The first one will be on contracts, then we'll talk about delegation later in the morning. So our first speaker is Jon Schneider, who will be talking about moral hazard and adverse selection in contracts. Please go ahead.
Thanks, Brendan. Yeah, so I'm going to talk to you about some recent work I and others have done on contracts with types. So if I was an economist, I'd probably say that this talks about principal-agent problems with both moral hazard and adverse selection. I'm not an economist, so I didn't even know what these terms meant until fairly recently. But in the setting of contract design, these terms actually mean pretty simple things. So moral hazard is this model we've heard about on the tutorial on Monday by Paul and Inbal. It basically just means you can't observe directly what actions the agent is taking in this principal-agent problem, only the eventual outcomes. So it's this hidden action model. Maybe some of you guys have seen in many of these talks. And the second fancy set of words is adverse selection. And this you're probably mostly familiar with from mechanism design. So adverse selection really just means types. It means that agents have some sort of private information in this principal agent problem. It'll mean that this private information affects the distribution over outcomes that their actions take. But in general, adverse selection just means that agents are different. And this is a nice way to model, for example, uncertainty about what agent you're facing if you're the principal trying to design a contract. And I guess, economists have studied these sorts of problems for decades. The main sort of novelty in what we do, and what like Paul, Inbal, and Tim have done in their original work on contract design, is that we study these problems through the computational lens. And I don't really know what the computational lens means, but for the purpose of this talk, it means that I'm only going to tell you about 2 types of results. So the first type of result is tractability. So basically I'm going to answer this question of, given some class of strategies for the principal, like the class of linear contracts or the class of menus of contracts, can we efficiently compute the best strategy in this class? And the second category of results are these approximability results. And here I want to take 2 different classes, compare linear contracts with optimal contracts, and ask how well do linear contracts perform compared to optimal contracts? Can we get some sort of approximation factor result? Can we say that linear contracts always get a constant factor approximation of the welfare, or a number of actions approximation factor of the welfare? Something like that. So these are basically the only 2 types of results I'll talk about in this talk. And a quick outline. So this talk is in many ways a direct follow-up to what Inbal and Paul talked about on Monday, but if you weren't there, no worries. I will do a quick review of the standard principal agent model. So I'll talk about the benchmarks that come up with the principal agent model, like linear contracts, optimal contracts, welfare, and I'll mention which are tractable, what the approximability results we know from Paul, Inbal, and Tim's paper in that model. And then I'll do the exact same thing in this principal agent model with types. So here things get more interesting. There's more interesting benchmarks for the principal. We can start thinking about things like menus of contracts and type-aware contracts, things like that. And then I'll do, again, the exact same thing. I'll tell you about the tractability of these different benchmarks and what we know about how these different benchmarks compare to each other. Okay. And then time permitting, if we have time at the end, I'll tell you 1 or 2 sort of other thoughts about how contracts with types relate to maybe some other problems in the algorithmic game theory literature. Okay, so the other thing I should mention is that most of this talk is based on a paper that I co-authored with Guru Gurganesh and Josh Wang, also at Google. But I'll try to also mention some other work that's been done in the area, most notably these 2 papers, one from last year's EC, one in this upcoming EC by Castiglione et al. And there's still lots of open questions in this area. Honestly, I think that the open questions are more interesting than what we already know, so I encourage you all to think about them, and I'd really like to hear what the answers to them are. Okay, so quick review of the standard principal agent problem. So again, this is what you maybe have already seen on Monday if you attended the tutorial then. But quick summary, there's 2 players, a principal and an agent. This agent will choose among some set of personally costly actions. And we don't get to see these actions because we're in this hidden action model, but each action will instead define a probability distribution over possible outcomes. And we, taking the perspective of the principal, will receive a reward that depends only on the outcome. So you can think of something like we're hiring someone to, I don't know, like invest our money or, or make an ad for us or something like that. And we don't get to see exactly how much effort this agent we hire puts in, but we get to see the eventual outcome of their work. And our reward depends on this eventual outcome, but the action the agent's hidden, and we need to incentivize them to take actions that result in good outcomes for us. So the goal in this entire line of work is to design outcome-dependent payment schemes, which we usually call contracts, to incentivize the agent to pay an action which is profitable for him or her, and also profitable for us, the principal. Okay, so notation-wise, we have the principal and the agent. The principal has m outcomes, which we'll call omega 1 through omega m, and each of these outcomes has an associated reward, r1 through rm. The agent, on the other hand, has n actions, which we won't be able to see directly, but that we will take. Each of the actions has some cost to the agent, so action a sub I has cost, let's say, c sub I. And each of these actions induces some probability distribution on the outcomes, which we'll denote by these capital Fs. Okay? And what the principal can do is we can try to incentivize the agent to play an action of our choice by implementing a contract. And a contract is just for every outcome, how much money we'll give the agent for that specific outcome. So this P sub I. Okay, and this is the third time we'll define the problem. This is the last time. But it's often nice to sort of put all these variables into a nice matrix representation. So on the left, we have the actions that the agent can take. On the top, the columns correspond to the outcomes that the principal wants to incentivize. And the elements of this matrix are sort of these probabilities f sub ij. One thing to note is that I'll usually assume that there's the existence of a null outcome and a null action. This basically means that the agent always has the option to do nothing, and this will deterministically result in an outcome which has 0 reward to the principal. This isn't like an important assumption, but it simplifies some things, and it's nice to have. And like I said before, a contract is just some assignment of non-negative transfers to the non-null outcomes without loss of generality. It's important here that the transfers are non-negative. This is usually referred to as this limited liability assumption. If you don't have this assumption, then you can do things like extract the full welfare of the agent, and the problem becomes a little bit silly. So we usually put this assumption in. Okay. And once we propose a contract, we assume the agent can see it, and the agent will best respond to the contract by picking the action that maximizes his or her utility, which is just the expected transfer they'll receive minus whatever cost the action has. Okay, great. So what can the principal do? So these are the benchmarks I mentioned in this standard principal-agent model. So one benchmark, which I already mentioned, is just this benchmark number 2, where the principal can offer just any contract to the buyer. Okay? But we want to compare this to other possible things the principal can do. So we can either restrict the set of strategies the principal can implement. So one natural set of simple contracts, also mentioned in the tutorial on Monday, is the set of linear contracts. So here the principal will offer payment proportional to the principal's reward to the agent. So basically, the contract will be of the form, hey, whatever I end up getting from this outcome, I'll give you 20% of this. Okay, and these are contracts we see a lot in practice, and that's one reason to study them, to try to explain why they're so omnipresent. And another pretty natural benchmark to consider is just the total welfare. So this is just the maximum over actions of the principal's utility plus the agent's utility. It's sort of like if we were some central planner and we could say, okay, the agent, you should do this, the principal, you should do this. This is the maximum total utility we can provide for everyone. This is also how much the principal can obtain if they get to cheat a bit. So for example, if they get to observe the actions directly and contract directly on the actions, the principal can extract the full welfare from the agent. Right? Question?
Just to make sure, so is that what the principal would actually want to do?
Yes, this is what the principal would actually want to do, because in this case, the principal can get the full welfare and the agent will get 0. I mean, the strategy is simple. The strategy is the principal looks at the agent with the maximum utility and says, hello agent, please play this action. I will pay you exactly your cost for this action. If you do something else, I'm not going to pay you anything. And then they get the full utility. Okay, great. So these are the three interesting quantities to look at in the standard principal agent setting. Okay, and like I said, now let's talk about what's tractable and how do these benchmarks relate to each other. So tractability is kind of boring in this standard principal agent setting. You can efficiently compute all three of these quantities, the optimal value for welfare, single contracts, linear contracts. The most interesting case is probably computing the optimal single contract, but even this is not too hard. Again, this was explained, I think, in several of the talks, but what you basically just do is for every possible action of the agent, you can find the best contract which incentivizes this action by solving a simple linear program. And then, since there's a small number of actions, you can just solve one LP per action and figure out what the best contract is. But as we'll see, this gets a little bit more interesting in the case with types. Okay. And then for approximability, these results are not trivial. These are from Paul, Inbal, and Tim's paper in EC 2019. It's known that sort of the relationship between any two of these benchmarks is theta of n. So the best linear contract gets 1 over number of actions fraction of the total welfare. And there are examples where this is tight. And there's also examples where linear contracts and single contracts are separated by a factor of n, and where single contracts and welfare are separated by a factor of n. And I won't talk about how they prove this now, but when I talk about analogous results for the case with types, you'll probably get some idea of how you can show these sorts of results. Okay. So that's all I want to say about the standard principal agent setting. Let's talk about what happens when you introduce types. So the setup is, again, very simple. Let's just take the exact principal agent setting in the standard model. And now we can assume that there's multiple, capital T, different types of agents. And at the beginning of this entire process, the type of agent is sampled from some distribution that's known to us. So it's this type theta over here. And this type theta affects their probability distribution over outcomes. So whereas before, if they took action A1, we knew exactly what probability distribution that would induce on outcomes. Now the probability distribution depends on what exact type of agent this agent is. Okay. And again, you can now think of this as, instead of me just giving you one matrix which specifies the probabilities, for every single type you have this matrix of probabilities distributions between actions and outcomes. So this is one example with two types. One thing to point out is that in this model I'm talking about now, I'm assuming that the costs and rewards of the actions and outcomes don't change between types, only the probabilities. It turns out this isn't an important assumption. Like all the techniques I mentioned can deal with the case where costs change between types, but it does change the results a little bit. So just to be concrete, let's just look at this case for now. Okay. And like I promised, the set of things the principal can do in the typed case is richer than in the standard case. So like before, we have the welfare, the single contract benchmark, and the linear contract benchmark. And these are the same. But now we have a couple other benchmarks that we can compare with. So one kind of natural thing to look at is this type-aware contract. So we say, okay, again, let's cheat a little bit. Let's tell the principal what the type of the agent is. So basically, the principal is just solving a standard principal agent problem per type, and ask, what's the best the principal can do this way? So basically, they'll give the optimal contract per type, get the optimal utility per type, and this is a sort of upper bound on what you can get with a lot of these other methods, single contract, linear contract. Another interesting thing which you can do in the case with types, which doesn't make much sense to do in the case without types, is you can offer the agent a menu of contracts. So you go up to the agent, you say, I don't know what your type is, but since I don't know what your type is, I don't know maybe what the best contract to offer you is. So here's a menu of contracts. Pick whichever contract appeals to you the most, and we will use this contract. And then the same thing happens after the agent picks this contract. The agent will best respond to the contract, choosing whichever action will maximize their utility, and the principal will get some reward. Okay. And you might notice there's this mystery benchmark. This is sort of a new type of contract introduced in this upcoming paper by Castiglione et al. If you're bored, I recommend you think about what could possibly be between menu of contracts and type-aware contracts. But I also want to stop for questions briefly here to ask if anyone has any questions about the model, either the standard one or the type one, before I proceed to talk about some of the results.
So in the previous one, we sort of implicitly assumed that the principle was this sort of proposed a contract, and that was sort of a take it or leave it.
Mm-hmm.
And now, at least with option 3, we've got a bit more of a interaction going on.
Mm-hmm.
If there's like a full negotiation between the principal and agents, does that sort of lead to more contract possibilities even in the base setting, or only once we have this type-aware setting?
I think it does not lead to anything more in the base setting. I'm not 100% sure, but I can't imagine that there's anything you could do other than just say, here's the contract, please best respond. I'll think about it, but yeah, I don't think there's anything else you can do.
You mentioned welfare, and I guess I missed the part about what the principal's trying to do. So is the principal trying to maximize their own utility minus their payment?
Okay, so there's two ways you can think of welfare. One is that this is not like a strategy for the principal at all. It's just like a property of the problem. It's just the maximum sum of principal's utility and agent's utility. The other way you can think of it is, let's say we let the principal cheat and see both the type and action of the agent. Then this is the maximum that the principal can obtain that way. And they can do things like say, okay, agent of type T, please play action A. I'll pay you your cost for it, and I will take all the utility. Jason?
I assume 3 is what we would call second best.
Good question. I don't know if there's like a established notion of second best for contracts with types. 3 could make sense.
So second best is the
Yes.
optimal thing you can incentivize in an information product.
Yeah. So I think 2.5 might count. I'll explain what 2.5 is later. So it's hard, yeah, like I don't want to get into it right now, but 2.5 doesn't require the principal to cheat, to know things they shouldn't. It does require kind of, like was mentioned, a little bit extra of a negotiation, but I think it would count as second best under that definition.
So if it doesn't know the type, you know the distribution of the types or something? Or?
So yeah, we know the distribution of the types. And for simplicity, maybe just assume it's uniform. It doesn't make much difference. What?
Yeah, sorry, do you mind reminding us exactly how the type influences the model?
Sure. So the only way the type influences the model in the framework I'm talking about right now is that the distributions over outcomes differ with the type of the agent. So just these probabilities f sub ij, they now have this dependence on theta.
And it can be arbitrary, so for each theta, totally different.
And it can be totally different, yeah. I know in Monday, Inbal mentioned a more restricted notion of types where just the costs depend on the type. And yeah, you get different sets of results if you put strong restrictions like that. Okay. One last question.
Sorry, just to clarify, so this subsumes the case where having the rewards depend on the types also allows you to have the cost depend on the types.
Yes. And we can even extend this to allow the cost to depend on the types. This is not a particularly strong restriction.
Thanks.
Yeah. Okay, great. So let me tell you about some things we know about the contracts with type setting, and also a lot of things we don't know. Okay, so first, like before, I'll tell you what we know about tractability of computing strategies for the principal in this type setting. And in this case, it's a lot different than the case with a standard principal agent model. So the strategies you'd like to implement, like some of the natural ones, like the single contract and menu of contracts, are intractable to compute in this setting. So we showed that it's APX hard to compute the utility of the optimal single contract or menu of contracts, even in the case where the number of actions is constant. So even if the agent only has 3 actions, there are situations where you can't do this unless P equals NP. Okay? This is via some reduction to dominating set that I won't get into, but I do want to point out the sort of partial converse, which is that you can compute the optimal contract in time polynomial in n to the t comma m, or in polynomial basically like something to the m time, right? So if either the number of outcomes or the number of types is constant, this is technically tractable, but as either m or like as m and t grow, this sort of problem is not solvable. And these sorts of algorithms are pretty simple. They're sort of the same LP style approach as before, where you ask, okay, let's pick a mapping from types to actions we want to incentivize. This is the best contract which incentivizes a specific mapping, and then we enumerate over all possible mappings, something like that. Was there a question? Oh, m is the number of outcomes, sorry.
I would have thought this as a problem would be a convex optimization problem, but I'm now surprised. Result for convex optimization.
Yeah, I think.
Do you have an intuition for why it's not a convex optimization problem?
I think the reason is that it's sort of the max of a bunch of convex optimization problems. And you sort of got this situation where you have a max of maxes, and this sort of thing is usually not tractable when you do convex optimization. There is something interesting I'll point out once we talk about this like mystery benchmark 2.5, but
Because the agent moves twice, first to report their preference and to act.
I think, okay, there's maybe a couple ways you could set this up as a convex optimization problem, but the most natural way that I know of is something of the form, okay, fix the strategy you want to introduce on the agent, so like the specific mapping from types to actions, and then ask what's the best contract which induces this. This is a small LP you can solve efficiently, but the problem is there's exponentially many such maps from types to actions, and it's not clear how to optimize over this in a nice way. And I mean, and this result shows that you can't. So, yeah, I don't have any stronger intuition beyond that, but I think that if you try writing out the problem, you'll see that it's not like not as convex as you would like it to be. Okay. And then one last thing I'll point out is like in this upcoming paper, they also extend some of these hardness results. I think you can show that maybe it's hard to approximate within any constant factor now. Okay. All right, so let me tell you about the second set of results, which is how these benchmarks compare to each other. So, like in the standard case, where we knew that linear contracts got a O of n approximation to the welfare, we can again show something similar in the type case, where we can show that the utility of the best linear contract is an O of n log t approximation to the welfare. And this also shows that the gap between any two of these benchmarks is in most O of n log t. I'll give a very quick overview of some of the ideas that go into this, but they're very similar to the ideas which go into the standard principal agent case. The main idea behind all these results is to look at the utility of the agent as a function of the contract you offer. So in particular for the case of linear contracts are parameterized by this one variable alpha, the fraction of your reward you give to the agent. And the nice thing about this is that the function u of alpha is really nice. So it's like a convex function because it's the max of a bunch of basically like linear functions for every action. It's also increasing. It also encodes the welfare in this case, which is very nice because u of 1, the case where you give all your utility to the agent, all your reward to the agent, just means that the agent sort of unilaterally optimizes the utility and they get the full welfare. So u of 1 is equal to the welfare. And you can also express the utility of the principal in terms of like a functional of this function u of alpha. So you can work out, it's not hard, that the utility of the principal is 1 minus alpha times the derivative of u at alpha. So you end up with a sort of functional analysis problem, which is you want to find the worst case function u of alpha, where the maximum of the principal's utility divided by the welfare, which is just u of 1, is minimized. And you can do that, and in general, if I let you pick like any convex function, you can actually make this arbitrarily small because this can correspond to like infinitely many actions. But if you have finitely many actions, you're restricted, like your function u is going to be a piecewise linear function with, at most n pieces. In the case with types, you get that it's like something like it has n times t pieces because each type contributes a different piecewise linear function to this u of alpha. Even this is enough to get some results. One nice lemma we have in our paper, which lets you sort of recover this n log t bound I mentioned, plus like a lot of the previous existing bounds, is we categorize sort of the worst case ratio of this in terms of the multi-set of gaps between y-intercepts of this, like the linear pieces in your piecewise linear function. Okay. So you get log of multiplicity terms, and it turns out in the case where you have contracts with types, you get like a sum of n log t terms this way. All right, and I won't go into how we prove this, but feel free to talk to me after the talk. Okay, and in terms of negative results, I won't say much about this, other than the previous analysis is tight, so it does also give rise to an example where linear contracts and welfare are separated by at least n log t. And we can show some sort of reductions to show that this sort of gap actually holds for like finer grained gaps in this like ladder of benchmarks. So for example, we know that the gap between the best linear contract and the best single contract is also omega of n log t, and the gap between like the best menu of contracts and the best type-aware contract is also omega of n log t. Okay, and these reductions are usually of the form, we designed the contract in such a way such that the stronger contract, like the type-aware contract, can get the full welfare, but the weaker contract can't do anything that a linear contract can. Okay. And you might notice that there is one thing I didn't mention here, and this is sort of a very interesting open question in contract design. It's actually the question which made us start thinking about this, and it's kind of sad that we couldn't resolve it, but I think it's a very natural question, which is how useful is it to actually offer a menu of contracts to the agent? So we know that it's like at least a little bit useful. We know that there's at least a constant factor gap between offering a menu of contracts and a single contract. And by the result I mentioned to you before, we know that the gap is at most n times log t. But other than this, we like know nothing about how this gap should depend on either the number of actions or the number of types. And I think even for structured cases, like the case that Mal mentioned on Monday, we don't really understand the power of menus versus single contracts. Okay, and then the last thing I should make good on my promise to you is I should tell you what this mystery benchmark is. Because I think this is really interesting. I recommend, this is also going to be presented at EC in a few weeks. I recommend attending the talk if you're there. But there is another type of strategy the principal can implement, which might not seem useful at first, but it turns out to have very interesting properties. So this benchmark is menus of randomized contracts. So what this means is that instead of the menus of contracts I described earlier are menus of deterministic contracts. I give the agent a choice of deterministic contracts. The agent picks one of these deterministic contracts and then plays best response to that contract. Okay? In this case, I will have a menu of distributions over deterministic contracts. And then I will first show this menu of distributions to the agent. The agent will pick one of these distributions. I will then honestly sample from this distribution and get a specific contract P. And then the agent, and then this is the contract we'll use. The agent will best respond to P, they'll play some action J, and then I will get some reward. Okay? So this seems a bit convoluted, but one thing which was extremely surprising to me is that unlike menus of deterministic contracts and single deterministic contracts, it is possible to efficiently compute the optimal menu of randomized contracts. So in some sense, this is the correct convexification of the convex problem you get from menus of contracts. And I mean, they show how to reduce this to some large LP with a bunch of constraints and show how to implement a separation oracle. I won't describe how they do it, but I recommend looking at the paper and attending their talk. But another thing I want to point out is that just like with the gap between menus and single contracts, I think basically nothing is known about how powerful this class of strategies are compared to either menus or single contracts or type-aware contracts, other that they lie between these two benchmarks I mentioned before. They're clearly more powerful than menus of deterministic contracts, and they're clearly weaker than type-aware contracts. Okay, how are we on time? All right, I'll mention this quickly. I just want to point out two sort of idle thoughts about how contracts with types relate to other problems in ADT. The first is just a coincidence that I noticed working on something else, So I want to point out that there's this connection between contract theory and the theory of Stackelberg games. So I won't go into like the formal definition of Stackelberg games, but you can think of it as take any game you want and you can turn it into a Stackelberg game by making one player the leader and another player the follower. And the idea is that the leader will move first, they will like announce their mixed strategy, and the follower will best respond to it. And these are like somewhat well studied in the AGT and TCS literature. I think historically they've mostly been studied in the perspective of security games, but there's other work too. And one very obvious connection is that contract design is a Stackelberg game. Like, the principal moves first, they announce their contract, and the agent best responds to it. And okay, this is maybe like a silly observation, but it's actually a fairly general Stackelberg game. I think it captures like a large class of like normal form Stackelberg games. And one thing I want to point out is that like some insights about contract design generalize to Stackelberg games and vice versa. So very recently in this completely like unrelated paper, this is a paper about learning in games, we used this result about the hardness of computing contracts to show that it's hard to compute Bayesian Stackelberg equilibrium. So it's hard to compute a Stackelberg equilibrium in Bayesian games because, a contract problem with types is a specific case of a Stackelberg game with types, a Bayesian Stackelberg game. So it seems likely to me that some other insights about contract design generalize to Stackelberg games, and it'd be interesting to understand what is this weird menus of randomized contracts? Does that have any analog in Stackelberg games? And the other thing I want to point out is that there's a lot of work in AGT about a monopolistic seller selling, some collection of items to several buyers. So it seems natural to ask sort of the converse question to this, which is let's say you're a buyer. How should a monopsonistic buyer set prices or design mechanisms to buy, possibly multidimensional goods from several different sellers? And one reason this question isn't maybe as commonly studied is that I think monopolies are a lot more common in real life than monopsonies. But if you go to the wiki page on monopsony, you can look at this list of monopsonies in practice. And the fact that labor is one of them indicates maybe that contracts are, there's some connection there already. But there's other non-labor related monopsonies too, including I think this Canadian Wheat Board, which was the sole buyer of wheat in Canada for several decades. Okay, so the connection I want to point out is that this sort of contracts with types framework already sort of gives you a natural framework for studying monopsonies. And the main thing to point out is that we always talk about distributions over outcomes, but there's no reason why these things have to be distributions or why the numbers in this matrix need to be probabilities. You can always sort of assume that this f sub I comma j is just it's not necessarily the probability that j results from action I, it's maybe just the total amount of good j that gets produced by production level I. So one question is sort of just, is this model interesting? And if it is, what sort of insights from contract design sort of translate over to studying monopsonies? Okay, that's all I want to talk about. Thanks for coming, and yeah.
Thank you. More questions?
Again, back to Jason's question. You said that single contract is hard to approximate. Are you saying, so single contract, is it posting transfers on each of the outcomes? Are you saying the outcome, the welfare is not convex in the prices, or?
Good question. So for this single contract benchmark with types, what I mean is the principal offers a single set of transfers. So for every outcome, they say, if this outcome happens, this is how much I'll transfer. And then each agent, depending on their type, will best respond to it differently. Maybe one agent, one type best responds by playing action I, another agent with a different type best responds by playing I prime, depending on their probability matrix. And you take the average utility you get over all types.
So this is non-convex in the price of each outcome?
It's definitely not convex in the transfer space. I mean, even for linear contracts, or even for the regular problem, the principal utility function is very non-convex in general. It's usually this piecewise linear
But
crazy
it is
to do.
convex in the lottery over the single contracts, right?
Even then, I don't think it's that simple. I think usually the principal's utility is not like easily expressible as a convex function in the principal strategy, like in the contract.
Okay, thanks.
So in multidimensional mechanism design, we get a lot of mileage out of a geometry over the type space. So for example, the characterization of incentive compatibility is the utility is convex in the type space. Your type space seems to be discrete and with no geometry. Is that correct? And would there be a way to get a geometry on type space that would make these problems easier?
Okay, yeah, good question. So this paper is sort of like, or these results sort of study the general case where, yeah, there's like, the type space is discrete, there's no like relation between them. I think one paper in the vein that you're describing is a paper that Inbal mentioned where their type space is like continuous and it affects the costs. So I think it's like the type is literally just like the cost per unit effort model. And there they can, find the optimal contract efficiently and things like that. But still there's like open questions there, like how useful menus of contracts are, or if you can find menus.
You mentioned these lottery contracts. Is that what you would get by applying the taxation principle to like a fully general randomized mechanism, or is that even more general than this?
My guess is yes, but I haven't thought this through very carefully. So I don't think there's anything more general than this you can do. But also, like before I saw this paper, I thought there was nothing more general you could do than offer like a menu of deterministic contracts. So I could be missing something.
I'm just curious, if you were allowed to do this, have you thought of anything that would be relatively simple that looks like this that you feel like might actually give you an improvement on just a linear contract?
So the question sort of like, would you expect to use anything which looks like this in practice? Like,
Yeah.
So on one hand, yeah, this looks kind of like weird. On the other hand, I think that, in real life contracts like, do depend on types. Like I think menus of contracts sort of model a case where, I don't know, you're like an employer and you have like multiple different positions that you like offer, right? And like the agent can like choose what position to apply to. And then, I mean, there's randomization on top of that, but like, maybe, you offer, when the agent comes in for a specific position, they know that they'll get some, randomly selected contract from a class of contracts. So it's weird, but I think it's not like unreasonably weird to me.
All right. Thanks again.
All right, great. Next up, we're going to have Tomar Ezra, who will be telling us about combinatorial contracts.
Hi. So I'm going to talk about combinatorial contracts, which was published in Fox last year. And this is based on a joint work with Thomas Kesselheim, Michal Feldman, and Paul Luting. So Paul already introduced this paper a bit in his talk 2 days ago. But here today we'll get into the proofs and the techniques that we use in order to show our results. So just let's remind a bit about the problems. So in contract theory, we ask the question of how to incentivize people to work. And running example is that you, as a website owner, and you want to hire a marketing expert, and the marketing expert can publish it in Facebook, in Instagram. It can take lots of actions. And we want to incentivize this marketing expert to exert effort in publishing the website, and we want to create a contract that will incentivize him. We don't observe the actions that the marketing expert do, but we only observe the final outcome and can motivate him using payments that are based on the outcomes. So let's try to model it a bit more formally. So we have the two entities. One is the principal and one is the agent. So the first thing that happens is the agent chooses an action. So this is the setting of the general setting of contract problem. These actions incur some cost for the agent, but and also gives a probabilistic reward to the principal. So here we assume that with probability f of a, the principal receives an award of 1. Okay, so far the agent has no incentive to do any action because he only incurs costs. So in order to incentivize him, we define a contract, which can be parameterized by a parameter alpha between 0 and 1. And this parameter is what fraction of the reward the principal gives to the agent. So, and now the game becomes like this. First, the principal commit to a contract, alpha. The agent, based on alpha, chooses the best action that maximizes his utility, and then randomized outcome revealed. And the agent incurs the cost and receives the randomized reward based on the outcome. So the utilities of the principal and the agents can be described. So the principal receives with probability fa a reward, but he gets only 1 minus alpha fraction out of it. And the agent receives alpha fraction of the reward, so alpha times fa, minus the cost c of a. Okay, so this is original setting of contract. And the question is how to find the best contract. So this is something that has been discussed in this workshop so far. Like you can run a linear program to each action to see how to incentivize it. And what we do in this work is consider combinatorial contracts. So in combinatorial contracts, the agent, instead of selecting just one action, he can select a set of actions, S. And this gives the combinatorial structure to the problem. Now what changes? So the reward is now 1 with probability that is a function of all the actions that the agent selects. And also the cost function is depending on the set. And this influences the utility. So this is the combinatorial structure. And we can reduce it to the problem of an original contract by just defining an action. Like the colors are not, okay. So just defining an action for each set of action. And in this way, we can define actions, like an action for each subset, and just increase the number of actions exponentially. And but we can reduce it to the case of agent that chooses only single action. But we lose twice in this process. First, the linear programming that we mentioned in order to incentivize an action now has exponentially many restrictions. And the second is that we need to solve exponential number of linear programming. So this is like we lose twice, and like you can solve it, but we are in computer science and we want to find it efficiently. So the question that we'll see today is in which cases we can solve it still efficiently, although without like going over all actions and finding the best one. Okay, so for the setting, we have n actions. We have cost. We assume that the cost function is additive, so for each action, for each set, the cost is just the sum of the cost of the actions. we have the success probability function, which is a combinatorial function, and we will assume that it is with a diminishing return, which is some modular in general, but specifically our main result is for the case of gross substitute, which I'll define in the next slide. And the goal of the principle or the problem that we're trying to solve is to find the best alpha. And what is the best alpha? The alpha that maximizes the utility of the principal, which is 1 minus alpha times f of s, where s is the best response of the agent, which is the set S that maximizes alpha f of s minus c of s. Okay, so let's define what is the type of f that we consider. So submodular is a very common definition in combinatorial auctions. So a submodular function is just such that the marginals are decreasing. So if for every action A, if I look at the marginal to a set S and the marginal to a set T that contains S, then the marginals to the bigger set is smaller. And gross substitute is a subfamily of submodular, which in order to define it, we first need to define a demand set. So a demand set is the line on the bottom that a demand set of a submodular of a gross substitute of any function and prices is the sets that maximizes the utility. The sets that maximize f of s minus p of s. Okay? And with the definition of demand set, we can now define what is gross substitute, which is, you can think about the following process. You have two vectors of prices, p and p prime. And p prime is bigger than p, coordinate-wise. And if we take a set in the demand of the lower prices, then there always exists a set in the demand of the higher prices such that actions that were in the former demand set that were not increased in P prime are still in S prime. So let's see an illustration of this definition. So for example, assume that we have 3 actions, and these are the prices or cost. Okay, and this is the demand set. Okay, the best actions for the best set of actions for the agents is the set S. Now, if we increase a few of the prices, for example, the 5 to 8, then now there exists a set in the demand that contains all former actions that were not increased. So the 3 stays in the demand. This is the definition of gross substitute. And a very useful property of gross substitute is that we can run greedy in order to find the demand set. Okay, so given any vector of prices or cost, we can calculate in a greedy way, each time adding the next action with the highest marginal, and we'll get a set in the demand. Okay, so our main result is that our main result in the paper is that for the family of gross substitute functions, we can find the optimal contract in polynomial time. And going beyond gross substitute, it starts to become hard. And we show that for budget additive, this is NP-hard. So there isn't hope to achieve using so gross substitute is the frontier of combinatorial contracts. And moreover, we show that it is possible to achieve for every function and to compute a FP task for it. But we assume that we have access to demand oracles, which is finding a set that maximize the utility of the agents. So if we know to calculate for every cost or for every alpha, it's enough. We have an oracle that gives us the demand set, which is the best response then we can have a FPTAS. And beyond the binary outcomes, we show that linear contracts are without loss of generality, max, min, optimal, and the proof of it is very similar to the proof of Paul, Tim, and Inbal for the case of non-combinatorial setting. Yes?
Is this FPTAS result new? I've seen the Oxford paper, I haven't seen this before.
No, this is in the original, like,
For every set function?
for every like function. Yeah, if you have a demand oracle, you can do it for every function. It was, I don't think that Thomas talked about it in the lecture in Fox. He had a shorter time, so, but I think it was written like in one of the lines, like, but he didn't describe it. Okay.
But just to make sure, it doesn't need to be submodular.
It doesn't mean what?
That doesn't need to be submodular for that.
No, you don't need some modularity. It's for general monotone functions.
Sorry, I might have missed it, but you've got budget additive in parentheses submodular.
Mm-hmm. So find the exact optimum is difficult. And also, okay, so there are two different models. Like you have the settings with demand oracle, and there are access model without demand oracles. So the NP-hardness is without demand oracles. Okay, if you don't have access to demand oracles, then you can only you can access the function f, then it's NP-hard to find the best action, but we didn't rule out the option to achieve approximation or FPTAS. For if you have demand oracle, then you can do FPTAS for every evaluation.
I actually don't understand the statement of moving to level 2, because I don't understand the first 4 words.
Okay, so the second is
What is budget additive?
budget additive is a subclass of some modular that are not gross substitute. They are in the
Got it.
okay.
Got it. Now I understand that.
Mm-hmm. So budget additive is not gross substitute, and this is the example that we construct that we show that it's NPR.
Just to understand why we care about gross substitutes on a function which is a probability. It's because you're doing a linear contract. So the agent reward is alpha times f, which looks like the value function, minus their costs, which look like prices.
Mm-hmm.
But the big,
Yeah.
usually when we're thinking about gross substitutes, we're thinking about moving prices. But actually, these costs are fixed. You're never going to move them. It's just that somehow this has nice structure.
So like gross substitute has many nice properties and structure. Like it makes sense for this problem to assume some kind of diminishing returns. Our goal in the beginning was to prove it for some modular functions, and we found the counterexample. And then we try to find the frontier in which we still can do it. And so like there is no specific reason why gross substitute is interesting, but there are many families of functions that do make sense, like k-demand or metroids that are subclasses of gross substitute that do make sense in the case of for a probability function. I cannot give you a specific reason why it must be gross substitute, but for many of subclasses of gross substitute, there are reasons that it makes sense that it will be. Okay. So next we are going to prove our main theorem, and so this our approach is looking in the upper envelope of the utility of the agent, and define sets of critical points, which will be the interesting points that define the contract that will help us to find the best contract. Okay, so what we do is for each set, we can write let's assume that the agent select to act upon this set. And we can write the utility of the agent as for each such set. Yes?
Sorry, guess which theorem you're proving?
What?
You had 2 theorems.
Theorem 1. I'm proving theorem 1. Okay? So for each set, we can define the utility of the agent as function of the contact if the agent decides to commit to this set. And we can define it for all the sets. We have 2 to the n sets. And then we can look at this, divide the interval of 0, 1 into sections in which the best response of the agent are the same. Okay, so in the first segment, it's the empty set, then the agent select the action 1, then 1, 2, and 1 through 3. And this is for an additive function. This example is an additive function. And so after we define this, so each of the sets starts at a point where if we set alpha equals 0, it's just minus the cost. This is the 1 point, and the slope is the value of f. F of s is the slope of each such function. So we can continue, we can look only in the upper envelope because these are the actions that the set of actions that the agent will do depending on the alpha. And then we can look at the principal utility, which is always decreasing up to the points in which the agent changes his best response. And we can look at these points, and these points we call critical points of the problem. And they're very, these are the points that we want to analyze. Okay, so we call these points critical points, and denote it by CFC. And a very simple observation is that the best contract is just one of these points, because after each point, the slope is decreasing, so you want to be as close as possible to the beginning of each interval. So we want to know, so with this in mind, a trivial algorithm is just go over all the critical points, critical alphas, calculate the utility of the principal for each such point, and choose the best one. Okay, so this is like the first thing that comes to mind. And in order to implement this algorithm, we need to show 2 things. We need to show that we know how to find the next critical alpha, if we are in some point on the interval 0, 1, we know how to calculate the next critical alpha. And we need, for this algorithm to be efficient, that the number of critical alphas won't be that big. So let's prove it. So the first thing, to show that you can find the next critical alpha, what we do is just run the greedy maximize utility of f with prices which are C over so alpha star. So we want to find the next critical alpha that is below alpha star, for example. And let's take an example where alpha star is 0.5, and this is the function. This is a gross substitute function, and these are the costs. So the cost of action A is 0.17, B 0.12, C 0.04. And so the first thing we do, we calculate the costs over alpha star, okay, and run greedy with this modified cost. Okay, so we begin with the empty set. Then the next action that maximizes the utility is A, then AC. So the greedy returns the set AC, and this is the set that maximizes the utility given these prices. The next thing we do is we look at all the branches of the greedy that he compared to. Okay, so instead of, for example, from the empty set to continue to A, the greedy might needed to compare it to either going to B, to C, or finish and end at the empty set, which means that no action has a marginal utility which is positive. And we calculate it for the all three. We calculate the all three for the greedy process. And the next thing we do is we calculate the alpha. So we assume that we arrive to this point of the greedy point, the greedy algorithm. We calculate what would be the alpha that will make you change to this action. Okay, so instead, for example, instead of going from empty set to A to go to empty set, from empty set to empty set, we need that alpha will be 0.34, and so on. So we calculate these alphas to each change, and we take the one that is maximal but below alpha star. And this is the point, the next point in which the agent will change his demand set, and we change it instead from AC to C. Okay, so this is how we can find the next critical point. And the second part of the proof is we want to bound the number of critical points. So the number of critical points for Gauss substitute functions are at most n plus 1 of choose 2. And like in the former example of the additive, we always added action. So in the beginning it was empty set, then 1, then 1, 2, and then 1, 2, 3. Now it's not the case anymore. Actions can come and go from the demand set. For example, here 1 enters, then it replaced by 2, and then we have 1, 2, and it might get in and out of the demand set multiple times. And in order to show that, to bound the number of critical points, we look at the observation that we mentioned earlier, that just maximizing alpha f of s over minus cs is equivalent to maximizing f of s minus c of s over alpha, which is what we used for also for the former proof. And it's equivalent to thinking of decreasing alpha as continuous inflation of the cost. So if you have the prices for 5, 3, and 2, then they increase gradually to 10, 6, and 4. Okay, so now to the proof. So in order to prove it, for simplicity, we first, for simplicity of the analysis, the claim is still true even if we don't do it, we first perturb the cost. Okay, we assume that the cost of the agent are not what we know, but we perturb it by smaller random amounts. You can think, choose arbitrary small epsilon and add a uniform 0 epsilon to each cost. And because of this perturbation, we get that for every alpha, no matter what, there won't be more than 2 sets that are in the demand. Because if there are more than 2 sets that are in the demand, like you have a collisions of random variables that are continuous, and this will happen with probability 0. Okay, so this is the main idea why we did it, and then we can differentiate between the 2 cases. Either there is only 1 set in the demand, which corresponds to cases for alphas that are not critical, and if there are 2 sets in the demand, then these are the critical alphas, where you change from 1 set to a different set. And so now if we look back at the greedy algorithm, so if we greedily adding the actions into the demand set, we have only one point of where the algorithm has, for the critical alphas, a tie break. And this tie break can do one of 2 things. It can either add a new action to the demand set that was already, if it was in the end, or it can replace one action with a higher cost action. And then it must continue the same as before, because otherwise it contradicts that there are more than two sets of in the demand of the subclass so far. Okay, so this is so with this property, we can now reorder the actions according to the cost. Okay, so because they are perturbed, you don't have ties, so we have a total order of them. And we can define the potential function in the following way. For the smallest cost action, we define the cost of 1, the second one 2, and so on. And the potential function of S is just the sum of potentials of the actions, and like the equivalent of the property that we said that either an action is added to S or an action with higher cost is replaced by action. An action with some cost is replaced by action with higher cost. It's trivial to show that the potential each time that we go to in the next critical alpha can only increase and strictly increases. And since the potential function is bounded between 0 for the empty set and n plus 1 choose 2 for the full set, we get that there are at most such n plus 1 choose 2 critical points. And now back to the, so far I cheated and I used the perturbation, but this is not a cheat because the limit of when I take the perturbation to 0 is the set of critical sets when I don't have the perturbation. And the only thing that can happen is that two critical points will converge to the same point and will merge. So I cannot increase the number of sets, the set of critical points, but can only merge them into a smaller set. Okay, so this is the main proof. So just to summarize, we show that for Gauss substitute, we can find the optimal contact, and this is the frontier. We cannot go beyond Gauss substitute using value queries. And this is a bit interesting because like you wouldn't expect that the Gauss substitute will like it's not definition that comes from contract theory, but from combinatorial auctions. And so this relation is a bit surprising. So the other results that I didn't talk about in this talk is that we showed that it's NPR for some modular functions using value queries. We have an FP task that uses demand queries, and linear contracts are like optimal in min-max sense, and all the results that I talked about here are either for success or failure. Like the rewards are either 0 or 1, but it extends to general binary outcome, non-binary outcomes. And like some open problems from this work is, so first, so we said that there is an FP task using demand queries, but is it possible to achieve even for some modular with demand queries the optimal contact? Like this is something that we didn't rule out. And back to value queries, like to understand what is the best that we can opt for, like whether it's possible to achieve a constant approximation or an FP task, not using demand queries. And of course, like this setting, like we saw in this workshop that the other dimension of extending to multiple outcomes, to multiple agents and multiple principles, we like to combine the combinatorial structure of the actions with those is also a very interesting direction. Okay, so that's it. Thanks. Yes.
Did you try supermodular?
Super modular. No, we didn't try to, like, the go-to of us were to some modular. This, we were thinking about if you know the paper of the agency contact model, where they assume some modular and wanted to do it for our setting. And this is, so this was the first thing that we've tried. And yeah.
Because demand oracles, we get them for free there, so.
Yeah, so for every settings that demand oracle are easy, then it makes sense that it will be also easier here. Like the demand oracle is very structured in the problem.
So going back to Jason's earlier question about gross substitutes, it sort of felt like, in the proof sketch at least, on the main things about gross substitutes you were using is sort of the optimality of this greedy approach to sort of constructing the sets. So I guess two-part question first. Was there another aspect of gross substitutes you were using somewhere that I missed? And the other one was, am I guessing correctly that the way the FP task works is you're basically going to replace the greedy step with using demand oracles and attempting to just find the optimal thing that way instead?
So for the first question, we use multiple properties of gross substitute. First, that you can run greedy, and like this is the most important one. And the second thing is that you can actually, like, it's very important that you can solve the demand oracle, even like here, like the greedy is the demand oracle, but you need both properties. So when we go to some modular and we have only demand oracle and not like the structure of the greedy, this is where we lose solving optimally, but can only, like the same techniques gives us the FP task.
I had a related question. So is gross substitutes and this greedy procedure working, is that an if and only if relation? Or if there was something where the greedy approach could be guaranteed to work, but it wasn't gross substitutes, would your results still hold in that setting?
So I think it's a characterization of gross substitute that a function for every vector of prices, the greedy returns the demand set is if and only if it's a gross substitute. You need, okay, so you discretize in a way that independent of the function. Like you don't need to know much of the structure of the function. Maybe for the limits or something, but not using heavily the structure.
Ascending auctions are often studied with gross substitute preferences. It's a very important family of preferences for ascending auctions. And it seems like what you're showing is the number of times the outcome changes in the ascending auction for a particular way of ascending the prices is a polynomial number. And so I'm wondering if, one, there's a connection to the literature on ascending auctions for gross substitutes that where other things like this might be known or where results like this might be important.
So actually we looked for like ascending prices for gross substitute. This is like like we didn't find places where you have that the prices are all ascending simultaneously. Like this is one of the key properties that we use, but we didn't find any other place where they use something that was useful to us for that all the prices are increasing in the same rate and like look at the demand set. At least I'm not aware of such a thing.
I see. I guess I thought something like that might happen. Like, I guess I thought you might be able to simulate something like that if you had two buyers. One of them had values that were basically proportional to those prices.
I mean, just to comment on that, I give it's been a long time, but my rough recollection is that a lot of the literature on ascending price auctions, there's a tendency to raise prices in a way that's like additively constant across the items rather than multiplicatively, just because that has like other nice properties about how the demand sets change. And so it wouldn't shock me if there's been a lot of work on that, but less on the multiplicative thing here, which is more related to linear contracts. So I second the idea that this might be an interesting thing. Like there might be interesting things here that have been overlooked in that literature. Yeah.
Okay, well, thanks again.
Great, so that's the end of the session. We now have a coffee break. We will reconvene here at 10:45.